Right now, your phone knows where you are, to within a few meters, not from the towers around you, from a handful of clocks floating 20,000 kilometers overhead. And here's the part nobody tells you. Those clocks are wrong, on purpose, because they're moving too fast and floating too high for time itself to tick the way it does down here. Ignore that. Ignore Einstein. And within a single day, your phone would think you're 10 kilometers from where you actually stand. So how does a slab of glass in your hand quietly solve a physics problem that took humanity's greatest mind to even describe? Let's build it up from nothing. Forget satellites for a second. Suppose I tell you just one fact. You are exactly 5 kilometers from a radio tower. Where are you? You can't say exactly, but you've narrowed it down. You're somewhere on a circle, 5 kilometers around that tower. Now a second tower, you're 7 kilometers from it. Another circle, 2 circles cross in just 2 points, you're one of them. Add a third, 3 circles meet at a single spot. That's you. This is trilateration, position from distances, not directions. But you don't live on a flat map. In real space, one distance doesn't put you on a circle. It puts you on a sphere, a whole shell of possible positions around the source. 2 spheres overlap in a circle, 3 spheres narrow that to 2 points, and one of them is usually out in space, easy to throw away. So in 3 dimensions, 3 distances pin you down. 3 satellites. Simple, right? It would be if we could measure those distances. But you can't hold a tape measure up to a satellite moving thousands of meters per second. So how do you measure that distance? Here's the trick. You don't measure the distance, you measure the delay. Each satellite is constantly broadcasting one thing: the time, right now, by its own clock. That message travels to you at the speed of light. When it arrives, your phone checks its own clock and asks, how long was that message in flight? A message that left at 12:00 and arrived 67 milliseconds later took 67 milliseconds. Multiply that tiny delay by the speed of light and you get the distance. Time times speed equals distance. That's the whole game. But look how brutal this is. Light covers 300 meters in a millionth of a second. So if your clock is off by just 1 microsecond, your position is off by 300 meters. Off by a millisecond and you're in the wrong city. GPS needs the time to within nanoseconds, billionths of a second. That's why every satellite carries an atomic clock. A clock so stable it would drift by 1 second only after millions of years. And that obsession with time is exactly where the trouble begins. We like to think a second is a second, the same for everyone, everywhere. Einstein is the one who broke that. First effect, motion. A GPS satellite races around Earth at about 14,000 kilometers per hour. And Einstein showed that a moving clock ticks slower than a still one. Not because the clock is faulty, but because time itself runs slow for things that move. For a GPS satellite, that makes its clock lose about 7 microseconds every day, compared to a clock on the ground. Now the second effect, and it pulls the opposite way. Einstein also showed that gravity slows time. The stronger the gravity, the slower your clock runs. Down here on the surface, we sit deep in Earth's gravity, so our clocks run a little slow. Up at 20,000 kilometers, gravity is much weaker. So a satellite's clock runs faster than ours, gaining about 45 microseconds a day. Put the two together, it loses 7 from its speed, gains 45 from the weak gravity. Net result, every satellite clock runs about 38 microseconds per day fast. 38 microseconds sounds like nothing. A blink is 100,000 microseconds. But remember the exchange rate, time into distance at the speed of light. 38 microseconds of clock error every day times the speed of light is about 11 kilometers of position error per day. And growing, so a GPS built by someone who'd never heard of Einstein would work for a few minutes, and then slowly and relentlessly place you streets, then neighborhoods, then whole towns away from where you actually stand. So engineers do something wonderful. Before launch, they deliberately mistune each satellite's clock, setting it to tick at the wrong rate here on the ground, so that once it's up there, moving fast and floating high, relativity nudges it to tick at exactly the right rate for us. They build the error in, so the universe cancels it out. Every time you get a location, Einstein's equations are already baked into the answer. There's one loose end. The satellites have atomic clocks. Your phone does not. Its clock is cheap, and always a little off, which remember would wreck everything. Here's the elegant part. That unknown error in your clock is the same for every satellite you're hearing. It's just one extra mystery number, and whenever you have one unknown, you need exactly one more equation. So instead of 3 satellites, your phone locks onto 4. 3 fix your position in space. The 4th pins down the exact time, cancelling your phone's clock error for free. Position and time solved together, so the next time your phone drops a little blue dot exactly where you're standing, remember what it took. 4 atomic clocks in space, a message riding a beam of light, and a correction for the fact that time itself runs differently up there than it does down here. Your phone isn't just finding you on a map, it's quietly, constantly proving Einstein right, a few billionths of a second at a time.